Well, I guess I did start it. Your tests are graded. If you'd like them, you all did quite well. When the worst grade was 90. uh, yeah. The homework for chapter 25 is due on the 15th. The homework for chapter 26 is due on the 27th. So continuing on with what we were covering, we've been talking about optics. So one of the things that happens with optics is that light will move at different speeds through different mediums. And when it travels from one medium into another and changes speed, because it's a wave, this side of the wave will slow down before this side, and the direction of the light will bend. So what you get is that if you could do some work with triangles, you can work out that V1 times delta t is going to be V1 times delta t over x here is going to be the sine of the incoming angle. And V2 times delta t over that same x is the sine of the outgoing angle. And this leads to sine of theta 1 over velocity 1 equals sine of theta 2 over velocity 2. So what happens is this change in speed causes a bending, you get refraction. And for refraction, we tend to use what's known as the index of refraction, which is the index of refraction is the speed of light over the speed of in the medium. So that gives you that index of refraction 1 times the sine of theta 1 equals index of refraction 2 times the sine of theta 2. Here is a video demonstrating that process of refraction.
First encounters a piece of glass, one side is slowed down before the other, forcing the wave front to change direction. This bending of light, whether in glass, water, or any other transparent material, is called refraction. Light is refracted closer to the direction perpendicular to the interface whenever it enters a medium that slows it down. This occurs no matter what the direction of incidence.
So your eyes use refraction to focus light on the back of your eye where you actually detect it. So the angle of refraction is related to the different speeds. And the speed of light in the medium is given by the index of refraction in that medium. So the speed of light in the medium is c over the speed of light is c over the index of refraction. Or the other way around is you can think the index of refraction is the speed of light over the speed of that light in that medium. So for example, if your index of refraction is 1.5, the speed of light in that medium is going to be 2 times 10 to the 8th meters per second. So this gives you that index of refraction 1 times sine of theta 1 equals index of refraction 2 times sine of theta 2. And index of refraction is the speed of light in a vacuum over the speed of light in the medium. And here are some examples of actual index of refraction. Diamond is about 2.24, 2.42. That's probably the highest you're going to encounter in visible light on a regular basis. Most materials are less than 3. And they're all over 1. Because if something had an index of refraction that was less than 1, that would mean that the speed of light in that material would be faster, would be superluminal, and that's against the rules. Glass varies, but regular glass is around 1.5, plate glass is 1.66, crown glass is 1.52, used quartz glass is 1.46, ice is about 1.31, water is 1.33, benzene is 1.5, ethyl alcohol is 1.36, vegetable oil is around 1.5 as well. And then carbon dioxide, for example, is 1.0045, and air is 1.000293. So the speed of light in air is basically the same as the speed of light in a vacuum. You know, we're talking 0.03% difference. Small difference. So how much time does it take for light to travel 1.2 meters in water? Speed of light in water, the index of refraction of water is 1.33. Oh, and C, the speed of light in a vacuum, is 3 times 10 to the 8 meters per second. Sorry. So, speed of light in a medium is C divided by index of refraction. So 3 times 10 to the 8th divided by 1.33. So the speed of light in water is 2.25 times 10 to the 8th meters per second. Speed is distance over time. So time is distance over speed. So 1.2 meters divided by 2.25 times 10 to the 8th meters per second gives you a time of 5.32 times 10 to the minus 9 seconds, or 5.32 nanoseconds. And it would take less time in air or some other medium. So we can write the angle of refraction in terms of the index of refraction. So you get index of refraction 1 times the sine of theta 1 equals index of refraction 2 times the sine of theta 2. This is the form that is primarily used because it's just a lot more practical. Numbers are smaller, they're just easier to work with. So when you have something going in from, say, air into water, some of the light will reflect, blah, 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 blah. So we'll bounce off the surface with an angle of incidence equal to an angle of reflection, and some will refract with an angle of refraction that is smaller than the angle of incidence because the index of refraction of water is larger than the index of refraction of air. And you get more refraction in diamond because diamond has an even higher index of refraction. So this compares water with 1.33 to diamond with 2.4 something. 2.46 or something like that. So some basic properties of refraction. When a ray of light enters a medium where its speed decreases, it gets bent towards the normal. When it enters a medium where its speed increases, it does the opposite. It bends away from the normal. There's no change in direction of propagation if there's no change in index of refraction, which is why if you put glass into oil, it appears to disappear because they have the same index of refraction. You can't see the transition. The greater the change in index of refraction, the greater change in propagation direction. If a ray of light goes from one medium to another along the normal, it doesn't get deflected, regardless of the index of refraction. Because basically it's the sine term goes to 0. So 0 times anything equals 0. Refraction can make objects that are immersed in water appear broken or bent. So if you've seen like a straw in water, it looks like it's bent. That's because of refraction. It can also create mirages. So the less dense air can bend the light up away from the ground, and that creates an image of an inverted tree or an image of the sky, which is why the roads, a hot road will look wet. Because the light gets bent above the road, and so what you're actually seeing is the sky. So that a few times actually yesterday when I was out running errands. So if a beam of light enters water, or n equals 1.33, or diamond, n equals 2.42 at an angle of 60 degrees relative to the normal, find the angle of refraction for each case. So remember, n1 times sine of theta 1 equals n2 times sine of theta 2. So here you can treat the index of refraction for air as 1. Because the difference is small enough that, you know, it's out the three significant figures, it is 1. So here, index of refraction 1 equals sine of theta 1. Sorry, index n1 sine theta 1 equals n2 sine theta 2. So sine theta 2 is going to equal n1 over n2 times sine theta 1. So if we're going into water, that's sine theta 2 will be 1 over 1.33 times the sine of 60 degrees. So the sine of theta 2 will equal 0.651. So theta 2 will be 40.63 degrees. That should have probably been 40.6, but whatever. Here, sine of theta 2 is 1 over 2. With diamond, it'd be 1 over 2.42 times the sine of 60 degrees. So the sine of theta 2 is 0.358. So theta 2 is 20.97 degrees. So it'd be 21.0 if you landed to 366. Here, while on a vacation to the Caribbean, you walk to the end of the dock and for no particular reason, you shine your laser pointer into the water. And when you shine the beam of water a horizontal distance 2.4 meters from the dock, you see a glint of light from a shiny object in the sandy bottom. Perhaps a gold doubloon. So if the pointer is 1.8 meters above the surface of the water and the water is 5.5 meters deep, what is the horizontal distance from the end of the dock to the shiny object? So this is asking for the distance from the end of the dock here to the shiny object. Yeah, and you know that you can figure out theta 1 from the fact that this is you're going out 2.4 meters and down 1.8 meters. So that can tell you the sine of theta 1. You can use that to find the sine of theta 2, where you're going down 5.5 meters and out some unknown amount. So I'll let you work on that for a minute or two, for a few minutes. So this is a bit of geometry, but basic thing is that n1 sine theta 1 equals n2 sine theta 2. So we can find theta 1 by taking the inverse tangent of 2.4 over 1.8, because tangent is opposite over adjacent. That gives us theta 1 is 53 degrees. So we'll find that sine theta 2 is 1 over 1.33 times the sine of 53 degrees, which comes out to 37 degrees. So theta 2 is 37 degrees. And knowing that theta 2 is 37 degrees, we can then find x, because the tangent of theta 2 will equal x over 5.5 meters. So x equals 4.1 meters. So 2.4 meters plus x is the distance. That will be 6.5 meters. Any questions? It's mostly just a bunch of geometry on top of that straightforward equation. So, well, one of the things that happens is we go from something with a higher index of refraction into something of a lower index of refraction. That angle from the normal is increased. Well, what happens when that angle is increased so that the sine of that angle is greater than 1? You can't have a sine greater than 1. Well, what happens is, if you're above the critical angle, where theta 2 would equal 90 degrees, you get what is known as total internal reflection. And you can find that critical angle. The sine of that critical angle is going to be into n2 over n1, where n2 is the lower index of refraction material and n1 is the higher index of refraction material. And this effect, known as total internal reflection, is used in a number of things. It's used in binoculars with a couple of prisms to extend the effective length of the tube, so that a binocular is actually longer. You're choosing a longer length to bring light into focus than you might think. It's also used in optical fibers to totally internally refract light inside the optical fiber. It's also used partially in things like diamonds and stuff to make them sparkling, the way you cut them. And there's also a special angle called Brewster's angle. What happens at Brewster's angle is that if you reflect light at Brewster's angle, it gets completely polarized. And this occurs when the reflected and refracted beams are at right angles to each other. And the direction of polarization is parallel to the reflecting surface. And the fact that light gets polarized when it reflects off of surfaces like this is part of why polarized sunglasses are so useful. They're designed to kill glare. Glare ends up heavily polarized like this. And so vertically polarized sunglasses help deal with glare. And Brewster's angle can be calculated using the appropriate geometry. It turns out you get that the tangent of Brewster's angle is n2 over n1. Where again, n2 is, in this case, the higher index of refraction material, and n1 is the lower index of refraction material. So here we have a prism. Notice how the surfaces here are not perpendicular to the ray of light. So after passing through this prism, would you expect the ray to be deflected upwards, downwards, or does it come out still horizontal? Which way do you think this prism will bend the ray of light that's entering it? Remember, this prism is at a higher index of refraction than the air around it. Yep. So what happens is that at the first index of refraction, it bends it closer to the normal, bending it down. But now it ends up on the other side of this interaction, which bends it away from the normal, which bends it down more. So by having that wedge shape and the angles between them, you bend it towards the fat end of the prism. So here, consider a sample of glass whose index of refraction is 1.65. So find the critical angle for total internal reflection for light traveling from this glass to air, where n is 1, and water, where n is 1.33. So the basic idea here is that n1 equals sine theta 1 and n2 equals sine theta 2. But at the critical angle, sine theta 2 is 90 degrees. So here, n1 times sine of the critical angle is going to equal n2 times sine of 90 degrees. Sine of 90 degrees is 1. So the sine of the critical angle is just n2 over n1. So the critical angle is the inverse sine of n2 over n1. So in the first case with air, that's the inverse sine of 1 over 1.65, which gives you a critical angle of 37.3 degrees. And with water, it's the inverse sine of 1.33 over 1.65, which gives you a critical angle of 53.7 degrees. Oh, well, we got time. I'm going to keep going then. So we can also form images like we discussed forming images with mirrors. We can form images with lenses. So lenses are used to focus light and form images. There are a variety of types. We'll consider only the symmetric ones. So for converging lenses, you can have convex meniscus, plano-convex, or double convex. We're going to look at double convex. For diverging lenses, you can have concave meniscus, plano-concave, or double concave. The double convex and double concave are just the simplest. You can think of a convex lens as consisting of a bunch of prisms. We can see how light going through it will converge at a focal point, assuming the lens is properly shaped. You can see how, we use prism to bend it towards the thick part. So if you just had a couple of prisms, you'd get light would be bent towards the thick part, but it wouldn't be focused. But by varying the shape, the curvature of the lens, you can get the light to converge to a focal point. And that curvature, a spherical curvature is good enough. Ideally, I think it's parabolic, but lens design gets complicated. Uh, and a concave lens can also be modeled by prisms. You know, the idea that it's spreading light apart. Again, light gets bent towards the thick part with lenses. So if you're drawing lenses, the three principal ways for drawing a ray diagram are similar to those for mirrors. There's the P ray or parallel ray that approaches the lens parallel to its axis. The F ray is drawn towards or through toward for a concave lens, or through for a convex lens, the focal point. And the midpoint ray goes through the middle of the lens. Assuming the lens is thin enough, it will not be deflected. And this is what's known as the thin lens approximation. So we will be using the thin lens approximation, where we assume our lenses are these ideal things, which basically just get defined by a focal length. So these are the principal rays for both types of lenses. For a converging lens, you have the parallel ray, which then goes through the focal point, the midpoint ray, which goes straight, and then on this side, the focal ray, which goes through the focal point and then becomes parallel. Here, for a diverging lens, you have the parallel ray, which looks like it came from the focal point, the focal point ray, which aims towards the far focal point and comes out parallel, and the midpoint ray, which goes straight through. As with mirrors, we can use these principal rays to locate the image. So here we have a diverging lens. The image is smaller than the object, closer to the lens, and virtual, and right side up. The convex lens will form different image types depending on where the object is located, with respect to the focal point. If an object beyond the focal point, you'll get a real image on the far side of the lens, which you can project onto a screen. And if you're between the focal point and the lens, you will get a virtual image on the same side of the lens as the object. That's what's going on with a magnifying glass. I thought I had a magnifying glass around here, but apparently gets shuffled off somewhere. Yeah. But a magnifying glass, basically you hold a magnifying glass within its focal length of the object you're looking at, so it makes it appear bigger. So the lens shown in the sketch on the left gets placed is generally used in air. If it's placed in water, does its focal length increase, decrease, or stay the same? And what do you think is the best explanation? We think the focal length increases because the lens has an index of refraction that is close to that of water, and hence it bends light less in water than it does in air. Does it decrease because the index of refraction of water is greater than the index of refraction of air? This results in more refraction and a smaller focal length, or the lens is the same and so the focal length is the same. You have a guess? It's actually the first one, because it has an index of refraction closer to water, it bends light less in water. So this dotted line here in the picture is what it would be in air, and it extends out further because the light bends less. So we can derive the thin lines equation the same way we did the mirror equation using these diagrams. And it ends up looking remarkably similar. In fact, it is 1 over dO plus 1 over di equals 1 over focal length. Basically the same. This is the thin lens approximation. And again, magnification is minus di over. However, the big difference between mirrors and lenses is that with lenses, when di is positive, it is on the opposite side of the lens from the object, because lenses let light through them instead of bouncing it back. So some conventions. Focal length is positive for converging lenses, convex lenses. It's negative for diverging or concave lenses, which is again opposite to mirrors. Concave mirrors are converging, convex mirrors are diverging. Magnification is positive for upright images, same orientation as object, and negative for inverted images, opposite orientation of object. That's the same as it is with mirrors. Image distance. Di is positive for real images. That's the same with mirrors. Real images are images on the opposite side of the lens from the object. Di is negative for virtual images, images on the same side of the lens of the object. That's the big difference from mirrors, where the real images end up. So with the lens, the real image is on the far side of the lens. With a mirror, the real image is on the near side of the mirror. So this projector uses a mirror. So the image, the real image, is on the near side of the mirror. The object is on the same side as the image. If you had a projector that used a lens, it would be out there, and the real, image would be on the far side of the lens. And then the object distance is positive for real objects from which light diverges, and negative for virtual objects towards which light converges. That's the same. So here, light produces a real image that is twice as large as the object, inverted and located 15 centimeters from the lens. On the object distance and the focal length of the lens. So the image, so di in this case would be plus 15, because the object is real, the image is real, inverted, and then m is minus 2. So you can use that to figure out the object distance. Well, I'll leave this up for a little longer so you can work on it. So, first step, we want to find the object distance. Well, it's inverted. We know that the object is inverted and twice as large. The image is inverted and twice as large as the object. That means our magnification is -2. And di over do equals magnification. So -2 equals minus 15 centimeters over do. Do is 7.5 centimeters. It's half as far away. Then, to find the focal length, 1 over do plus 1 over di is 1 over the focal length. So 1 over 7.5 centimeters plus 1 over 15 centimeters is 1 over the focal length. So 0.2 inverse centimeters is 1 over the focal length. So the focal length is 5 centimeters. Here we have an object placed 12 centimeters in front of a diverging lens with a focal length of negative 7.9 centimeters. We want to find the image distance and the magnification. So here we use the thin lens equation, 1 over do plus 1 over di equals 1 over the focal length. So 1 over 12 centimeters plus 1 over di equals 1 over minus 7.9 centimeters, because the focal length here is negative. 1 over di is going to equal minus 0.21 inverse centimeters. So di is minus 4.8 centimeters. Magnification is minus di over do. So minus 4.8 centimeters over 12 centimeters is 0.4. And then we have dispersion and the rainbow. So it turns out the index of refraction will vary slightly with the frequency of light. In general, the higher the frequency, the higher the index of refraction. Not always the case, but that's the general case. The actual thing depends on the material. This means that reflected light gets spread out in a rainbow of colors. This phenomenon is known as dispersion. So choosing the right material, choosing surface coatings and things can reduce this effect. They spend a whole lot of money with camera lenses to minimize this. This is what's known as chromatic aberration. Correcting this can be expensive. This is why camera lenses are so complicated. Part of why camera lenses are so complicated. But this is known as dispersion. And reducing dispersion is something you want to do for a lens, but you can maximize it for a prism to create a rainbow. And an actual rainbow is created by the dispersion of light as it refracts inside a raindrop. So this is what's going on inside the raindrops. How you get what you actually see is a whole lot more complicated. Because what you're looking at is the combined light from lots of different raindrops. And the color you see depends on the angle you're looking at compared to the angle of the sun. Because, like violet light comes out at 40 degrees here, while red light comes out at 42. But that is what's going on. In the individual wave drop, you're getting dispersion like this. And as the drop falls, all the colors of the rainbow arrive at the eye. So you have a ton of raindrops, individual colors come from each section of them. There's also some interference effects. And sometimes you get a faint secondary eye, the double rainbow. You may have, well, you guys might be too young for that. But the double rainbow actually comes from more reflections inside the raindrop. So the standard raindrop you see is one reflection. The second rainbow is 3. Because 2 reflections goes on the other side. So you'd have to be looking the other direction to see it. So this is the end of chapter 26. A wavefront is a surface along which the wave phase is constant. Rays perpendicular to wavefronts indicate the direction of propagation. The angle of incidence equals the angle of reflection. The image formed by a plane mirror is upright, but appears reversed left to right. Appears to be the same distance behind the mirror as the object is in front of it, and is the same size as the object. Spherical mirrors have spherical reflecting surfaces. A concave mirror is curved inward, and a convex one outward. A convex mirror has a focal length of -half the radius for a spherical mirror. A concave mirror has a length of +half the radius. An image is real if light passes through it, virtual if it does not. The mirror equation is 1/do plus 1/di equals 1 over the focal length. Magnification is -di/do. Refraction is the change in direction of light due to a change in speed. The index of refraction gives the speed of light in a medium, where speed of light is the speed of light in a vacuum over the index of refraction. Snell's law, thus index of refraction 1 times the sine of the angle sine θ1, where θ1 is the angle from the normal, equals index of refraction 2 times sine θ2. A light entering a medium of higher n is bent towards the normal. The light entering a medium of lower n is bent away from the normal. When light enters a medium of lower n, there's a critical angle beyond which the light will be totally reflected. The critical angle, the sine of the critical angle is n2 over n1, where n2 is the lower, the medium of lower index of refraction. And at Brewster's angle, the reflected light is totally polarized, and the tangent of Brewster's angle is n2 over n1. And a lens uses refraction to bend light and form images. And the thin lens equation is 1/do plus 1/di equals 1 over the focal length. And magnification is -di/do. The index of refraction will vary with frequency. Different frequencies of light are bent different amounts. This is called dispersion. And rainbows are caused by dispersion within raindrops. And that's the end of the chapter. I'm going to stop sharing.